Hello and welcome back, everyone. So moving on to, rather than techniques of integration, techniques of summation. We're just going to apply partial fraction decomposition to sums now instead of integrals. Of course, that portion of today's topic will be the same as it felt with integrals. We do, however, have to discuss really the power rule for sums, because we've had a few power rules for sums. Let's see if we can recall them. One of them looked like n to the underline k, right? And this was called the falling factorial. And the power rule here said that the output was n to the k plus 1, but with an underline, and then divided by k plus 1. So it looked exactly like our power rule for integrals, except we had to use this falling factorial notation instead of regular powers. And then the power rule with regular powers took the form that I have in the middle here, where if you sum n to the k, it looks like the sum from j being 0 all the way up to k being this power, right? Same k on both sides, as well as the same k out here, as well as the same k down here. Okay, so a few different k's sitting around. You take the sum, you have your binomial coefficients, those come from Pascal's triangle. There were these negative Bernoulli numbers, which themselves have a pretty nasty definition, which has two sums for each of those, as well as n to the j plus 1 over j plus 1. Now, importantly, if you look at the very top case, the case when j is equal to k, you do have the lovely case of n to the k plus 1 divided by k plus 1 that you would want, but you pick up so many other terms. And so this was kind of a nasty formula to work with. It is, unfortunately, a formula that we kind of have to use still with partial fraction decomposition. We're going to see how we choose to sidestep that here. There's going to be a better notation we use to kind of say, yeah, we're using this formula, but let's throw it under the rug for a bit. Unfortunately, we cannot use the lovely actual power rule we want with this falling factorial. It's just not going to work with partial fraction decomposition. Anyway, to that end, I do want to make a very important note about the power rule we see in the middle of the screen. And that note is if I put a negative number in for k, let's say negative 2, for example, well, number one, this sum starting at 0 and ending at negative 2, you could probably interpret that a specific way, maybe go 0 to negative 1 to negative 2, but usually it's not defined. You usually only start, the lower bound is always less than the upper bound. And especially right here, if you try to compute the binomial coefficient with a negative, well, it'll end up giving you a lot of infinities, which can make your life hard. So we're dividing by 0, in other words. So that's going to make your life incredibly hard. In other words, it means this just does not apply for negative k. And that's not going to be good, because let's think about how partial fraction decomposition works. The whole point of it is to analyze rational functions. For example, something like n plus 1 over 2n squared minus 3n plus 2. Right, partial fraction decomposition would decompose the rational function into the sum of ajk over x minus bj plus ... over the roots of the denominator. And so you'll have these kind of non-trivial denominators show up like I have here, and those are going to have to be summed, right? So at the end of the day, we're going to require some sort of a summation formula for 1 divided by n to a specific power. So our current power rule can't handle that. What are we going to do instead? We're going to define what I have in the middle here, which is technically a proposition. It's not necessarily a definition, but we are actually interpreting it as a definition for now. So the generalized first power rule for sums can be defined by the following. So we've kind of modified things away from sums and Bernoulli numbers. What we're doing now is we're going to take this k that's in the power, and we're going to end up putting it in the power of a derivative, and then we're going to take this n, which is the term we sum over, we're going to put it in the power of an exponential. There are some other terms in this formula, right? We've got e to the x minus e to the nx divided by 1 minus e to the x. But in general, we're thinking that this power k goes in the power of derivatives, and the n that we're summing over goes in the power of one specific exponential. And we're going to take k derivatives of that function, and then we're going to go ahead and let x go to 0 in a limit. It's going to 0 from the left, so it's going from negative numbers like 0.001, 0.0001, and so on, all these negatives. And it turns out if you compute that, that's why I'm calling this a proposition, because if you do compute it all the way out, what does that limit compute toward? It computes as the sum starting at 1 up to n minus 1 of m to the k. And so that's one possible indefinite sum of this left-hand side. Remember, just like antiderivatives, there's infinitely many possible of them. But we're going to go ahead and define this sum, which happens to be equivalent to actually computing this limit out. We're going to define that to be the power rule. Now, what do we get out of this power rule is we get the ability kind of, let's imagine what it would mean to do negative k's. question mark? What would maybe d to the negative 1 over dx to the negative 1 mean? Or maybe d dx to the negative 1. This is the inverse, right? Inverse of the derivative. What is the inverse of the derivative? We should really interpret negative k as k antiderivatives. Okay, so we're going to be seeking antiderivatives of this function if I decide to make that k negative. And that's an easy enough thing to compute. We have to be a little bit careful when we compute antiderivatives because they're not unique. So I have this little footnote that says the constants in the antiderivatives must be chosen so that the functions decay to 0 as x goes to negative infinity. It's an easy enough thing to do. You would find out how to do it if you decided to compute the antiderivatives. We're actually going to avoid computing all of these things today. We're just going to make this a definition and work with it for the rest of the day. We also get away with something else that's kind of nice here. If I decide to take this n and I shift it maybe by, let's shift n by 6, for example, and I take this n and I replace that n with n minus 6, everything still works out, right? It doesn't matter if I replace that power with an n minus 6. So this is kind of invariant under shifts, which is what we know from reindexing at least indefinite sums. So that's a nice thing that's happening here. We're going to define it that way. We're also going to define something called the generalized harmonic numbers. The generalized harmonic numbers are a doubly indexed sequence h sub n and k, and it's not really a surprise that these are similar to the n and k we have already seen. But how does it work with the harmonic numbers? Well, we put a negative sign in front of k, and in fact, this function's been modified very slightly. If I decide to distribute this e to both terms there, we find out that really our power rule that we just looked at in that proposition corresponds to an n minus 1 in the first entry of h, and it corresponds to a negative k in the second entry of h. So not exactly the same as each other. You kind of have to say, okay, if I'm going to do the power rule here, it's going to be h n minus 1 negative k. Or in the event that we're doing a lot with rational functions today, the whole point of partial fractions, we're going to see a lot of these kind of reciprocal powers show up. And when it's a reciprocal power, you're just going to get h of n minus 1 comma k. And so in some sense, these are what we want to focus on today as our power rule. This is our power rule for partial fractions. In some sense, we're introducing a new function. You know, way back in the day, the first time somebody told you about the natural logarithm, you had no idea what it was, you didn't know how to work with it. It was just a new function that you'd never experienced before. That's what we're doing with this h. It's just a new function. We haven't experienced it very much yet. It has the really useful property that it allows us to perform these sums of reciprocal powers. So we're just going to call these the generalized harmonic numbers. They do happen to be computable. You know, if we go ahead and use this limit, we just won't worry about computing them explicitly. So I'm going to say that now. We won't worry about computing h and k explicitly the same way we don't worry about computing the natural logarithm of 2, for example, right? Nobody really asks you to compute the natural logarithm of 2. You agree it exists, and you use the natural logarithm function without necessarily needing to know how to compute it. So that's what we're going to get away with these generalized harmonic numbers. We're just going to use them as kind of this function which can appear as the sum of the reciprocal powers as well as regular powers. So that's what we're going to use today, these generalized harmonic numbers. And we can immediately use them to state this lovely proposition, which is to say that all rational functions are summable using partial fraction decomposition. Right? In our case, if we look at the indefinite sum of any rational function, so that's a ratio of polynomials, so I've got two polynomials here, we'll always be able to actually perform this sum in closed form, you know, up to the generalized harmonic numbers, using partial fraction decomposition, a linearity of summation, and the generalized first power rule for summation. And when I say generalized first power rule, you can either interpret it here, which is the one that I like to think about. Really, that's the generalized first power rule. Or you can interpret it in our proposition here, where we compute it directly using that limit. Either one's perfectly fine, but you use it to show that all rational functions are summable. Okay, so let's look at the first example of this, and the partial fractions portion should feel familiar. It's only been about a week since we studied partial fractions, and actually we've been using it with trigonometric functions as well. So in terms of partial fractions, we should be able to analyze this rational function pretty easily. I'm first going to note that because the degree of the numerator is less than the degree of the denominator, we don't need to perform polynomial long division. And we can just go straight to factoring the denominator. Now, how would I factor this denominator? This one I wrote out so that you could factor it by sight, but maybe if you don't see what the factor should be, let's use the quadratic formula. That's going to give me what? Negative b plus or minus the square root of b squared minus 4ac all over 2a, so that'll be 1 plus or minus root, well, that's 1 minus negative 24, 1 plus 24 is 25 all over 2. We're looking at 1 plus or minus 5 over 2, also known as negative 4 divided by 2, negative 2, or 6 divided by 2, which is 3. Now we factor as n minus a factor, so minus negative 2 will be plus 2, and n minus a factor, n minus 3. So that's how we're going to factor the denominator to n plus 2 and n minus 3. Then partial fractions say we get to split the actual rational function at the factors in the denominator. Now, we don't necessarily know what those two coefficients are going to be, but we can go ahead and solve them by performing a common denominator and adding everything together. The first term, a11 over n minus 3, is missing kind of the denominator of the second term, so we'll multiply by n plus 2 over n plus 2. Similarly, in the second term, a21 over n plus 2, that's missing the denominator of the first term, n minus 3 times n minus 3. So if we go ahead and perform our common denominator, our new numerator will be a11 n plus 2 plus a21 n minus 3, and then we're going to expand everything, so distribute the a11 and distribute the a21, and what do we end up with? Well, a11n plus 2a11 plus a21n minus 3a21. If we group all terms with n together, a11 plus a21n, group all terms that are constant, 2a11 minus 3a21. We're comparing all the way back to where we started, 3n plus 11, so we need that to be 3 times n plus this to be 11. So there's going to be my system of equations where a11 plus a21 is 3 and 2a11 minus 3a21 is 11. If I solve the system of equations, the first line is telling me a11 is 3 minus a21, and then I can use this definition of a11 within the second line to tell me that, well, 2 copies of 3 minus a21 minus 3 copies of a21, which will end up simplifying to 6 minus 5a21, has to be equal to the right-hand side, 11. If I subtract 6 from both sides, you get negative 5a21 is 5, or in other words, a21 is negative 1. If a21 is negative 1, I just look all the way to this line again. I have 3 minus negative 1 for a11. In other words, a11 is 4. So I found my two coefficients. They happen to be 4 and negative 1. And that's allowed me to perform the partial fraction decomposition, which means that this sum is actually equal to this sum. And because of linearity of sums, the 4 can come out, the negative 1 can come out, and the sum can go to both terms on the inside. So here's my 4 out front, my negative 1 out front, and the sums on both terms on the inside. Now I have to actually compute the sum here, and this is where that new power rule is going to play a big role. Recall the definition of the generalized harmonic number. If I'm doing something like n to the k, this is h n minus 1 comma negative k. Okay? So h n minus 1 negative k, that means whatever goes in here needs to take the place of n. So this entire n right there is replaced with n minus 3. That's why we have n minus 3 minus 1, because the power rule over here had a minus 1 on it. Same deal over here where I have n plus 2. I have an n plus 2, but then I still need to include the minus 1 because this h had a minus 1 on it. Okay, and then when my power here, k, when the power is negative 1, well, I'm going to have a negative, negative 1, also known as a positive 1 on both of these h's. So if I simplify the subscript a little bit, first subscript is negative 3 minus 1, also known as negative 4, and the second subscript is plus 2 minus 1, also known as plus 1. And so we can say in terms of the generalized harmonic numbers that this sum is equal to 4 hn minus 4 comma 1 minus hn plus 1 comma 1 plus c. That's how we would use partial fractions to sum a specific rational sum. We can do the same thing with yet another case of partial fractions, where in this case our denominator will be n squared plus 7n plus 12. And if we go ahead and factor the denominator, our numerator is 1, so we're really not worried about it. But the denominator, let's run a quadratic formula on that really quick. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Looks like negative 7 plus or minus 49 minus 48 will just be a 1 all over 2. Looks like I'll have negative 8 over 2, also known as negative 4, or negative 6 over 2, also known as negative 3. And recall factoring will always be n minus a root, so minus negative 4 will be plus 4, and n minus a root minus negative 3 will be plus 3. So we can factor to n plus 4 and n plus 3. And when we do that, partial fraction says we're going to split at the factors, so we split at the factors, and we need to find a11 and a21. To find a11 and a21, we're going to form a common denominator. Well, in my first case, a11 over n plus 3 is missing the n plus 4 from the denominator. My second case, a21 over n plus 4 is missing an n plus 3 in the denominator. And so if I go ahead and multiply by those and form the common denominator, my new numerator will be a11 n plus 4 plus a21 n plus 3. If I distribute everything and rearrange, group my terms with n, I'll have an a11 plus a21 n, and I'll have a 4 a11 plus 3 a21 for my constant term. If I go back to the beginning, it's a 1, or in other words, 0n plus 1. And so this first a11 plus a21 I'm going to pair with a 0, and then the 4 a11 plus 3 a21 I'll pair with the constant 1. That forms my system of equations where the first is equal to 0 and the second is equal to 1. If I decide to solve this system of equations, I'm going to rearrange the first into a11 as negative a21. Then once I know that a11 is negative a21, I'm going to go ahead and grab it and plug it into the second. When I plug it into the second, I'm going to get 4 times negative a21 plus 3a21, which ends up just being negative a21 is equal to 1. Well, if negative a21 is 1, then positive a21 is negative 1. And if a11 is negative a21, then a11 is positive 1. So therefore, I can actually decompose 1 over n squared plus 7n plus 12 into 1 over n plus 4 minus 1 over n plus 3, the minus sign coming from the coefficient for a21. Therefore, I can go ahead and actually rewrite my sum as the sum of 1 over n plus 3 minus 1 over n plus 4. And then I want to bring up that while we could immediately use the generalized harmonic numbers to solve this sum, we could also be a little bit more clever. A few days ago, if you didn't know about the generalized harmonic numbers, you would still be able to sum this, and I know you would be able to sum it because this is a telescoping sum. So let this be just a little bit of a note that a lot of partial fraction sums will decompose into telescoping sums. I'm just going to write that down here in parentheses. A lot of partial fraction sums will decompose into telescoping sums. So in this case, let's go ahead and use telescoping sums to find the sum here. Well, let's recall what we want for a telescoping sum. We want something like an minus j for some specific an. Well, here, because 4 is bigger than 3, we're actually going to call an 1 divided by n plus 4, and actually we're going to call an negative 1 divided by n plus 4, which makes a positive 1 over n plus 3, well, 3 is 1 less than 4, so that would be an minus 1 will be negative 1 over n plus 3. And then you can rewrite the sum as negative 1 over n plus 4 minus negative 1 over n plus 3. There's our telescoping sum. The telescoping sum rule says what is it equal to? Well, when you have an minus 1, it's always equal to an minus 1 plus c, and we know what an minus 1 is. It's right there. So this is equal to negative 1 over n plus 3 plus c. That's how we would solve this using telescoping sums, and I do actually go through that here, and I get negative 1 over n plus 3. But if you want to be a little bit lazy and just get away with the generalized harmonic numbers, you certainly can. So I've taken my sum and distributed it to both terms. There's the generalized harmonic number for n plus 3 minus 1, and then because of this power is negative 1, that's a negative 1 there. And then I have a minus, this is the generalized harmonic number for n plus 4 minus 1, because that's a negative 1 power, I have a negative 1 there. If I simplify those a little bit, you get hn plus 2 comma 1 minus hn plus 3 comma 1. Now maybe you might ask, are these two equal to each other? They had better be equal to each other because there's two sides of the same coin. Let's see why they're equal to each other. Well, this difference of harmonic numbers that I got right away, if we factor a negative sign out, what do we actually have? We have hn plus 3 minus hn plus 2. Well, let's recall what the finite difference was. The finite difference just adds 1 to n, so that would make it n plus 3, and then it subtracts it by itself. It's going to be n plus 3 minus n plus 2. And so we can rewrite the answer we got for the harmonic numbers as the negative of a finite difference of a harmonic number. And if we think about how harmonic numbers are defined as the sum of reciprocals. And so this harmonic number is just the sum of a specific sequence. What happens when you take the finite difference of a sum of something? That's exactly the fundamental theorem of discrete calculus. The finite difference and the sum cancel each other, and we're just going to get 1 over n plus 3, but because of that minus sign, we're going to have a minus sign there, and we're going to get negative 1 over n plus 3. So it does perfectly agree as you'd expect because of the fundamental theorem of discrete calculus. Let's do one more example, and then we're going to finish. So this example is a little tricky because we do indeed have a ratio of functions where the numerator has higher degree than the denominator. And when the numerator has higher degree than the denominator, we're going to have to do polynomial long division. So I've changed the variable to x instead of n here, just because that's the way polynomial long division works better in my head. But if you want to do it all in the variable n, go right ahead. How are we going to do this? Well, we're going to take the denominator. Here it is. We're going to divide the denominator into the numerator. There it is. And how are we going to get x squared to give me negative 2x cubed? Well, I'm going to have to get there by a negative 2x. If I go ahead and get there with a negative 2x, then that negative 2x is going to come by and it's going to multiply the x squared, it's going to multiply negative 4x, it's going to multiply 3, and I'm going to subtract everything off, so my signs are going to flip. I'll have a 2x cubed, I'll have a negative 8x squared, and I'll have a 6x. That's going to get added to everything above. When those get added to everything above, well, these are going to cancel. That's the entire point. I'll have 6 minus 8, so that's going to give me a negative 2x squared. I'll have a 2 plus 6, that's going to give me 8x, and then the minus 5 doesn't have anything added to it, so that'll just come along for the ride. In my second step, I'm going to ask how many times does x squared minus 4x plus 3 fit into negative 2x squared plus 8x minus 5. I'm going to have to get the leading terms to agree. How do I get x squared to equal negative 2x squared? Well, I multiply it by negative 2. When I multiply that by negative 2, my negative 2 is going to multiply all three terms here. Then my signs are going to flip because I'm going to be subtracting it from the above. I'll get 2x squared minus 8x plus 6. And if I add everything above, then the 2x's cancel. I have an 8x and a negative 8x that cancel. Negative 5 plus 6 gives me a remaining 1, also known as a remainder of 1, right? So my polynomial remainder will be the numerator in what remains, which will just be a 1, and the denominator comes along for the ride, the original denominator being n squared minus 4n plus 3. And so altogether, polynomial long division tells me that I can divide out a 2n minus 2, and what I have as a remainder is a 1 over n squared minus 4n plus 3. Now this final term, 1 over n squared minus 4n plus 3, will be what I perform partial fractions on. So now when it comes to that 1 over n squared minus 4n plus 3, I'm going to perform partial fractions by factoring the denominator. Maybe if you don't see how to factor, let's run the quadratic formula on it. We're going to do negative b plus or minus the square root of b squared minus 4ac all over 2a. That's going to be 4 plus or minus 16 minus 12 is 4, square root of that is 2. All over 2, also known as 6 over 2, that's a 3, or 2 over 2, that's a 1. So I'll have an n minus a 1 and an n minus a 3 in my factor. Partial fractions lets me split at my factors, so I split at my factors, and now I find my new coefficients, a11 and a21, by common denominator. If I actually go through the work of the common denominator, my first term is missing the denominator of the second, so I'll multiply by n minus 3 over n minus 3. And the second term is missing the denominator of the first, so I'll multiply by n minus 1 over n minus 1, and then combine my numerators, and I get a11 times n minus 3 plus a21 times n minus 1. If I expand and regroup all the terms there, I'll have an a11 plus a21 times n, as well as a negative 3 a11 minus a21. Comparing back to where I started, this 1, it's really 0n plus 1, right? And so the 0 will have to agree with a11 plus a21, and the 1 will have to agree with negative 3 a11 minus a21. That's where I end up with my system of equations from. And I'm going to go ahead and solve my system of equations by solving the first line, which tells me a11 is negative a21, plugging in that negative a21 for a11 in the second line. That's going to give me negative 3 times negative a21 minus a21, which simplifies to 2 copies of a21 equals 1. Well, if 2 copies of a21 equals 1, then a21 by itself must be a half. And if a11 is negative of a21, a11 must be negative a half. Altogether, that says that my partial fractions decomposition of 1 over n squared minus 4n plus 3 has coefficients of negative 1/2 and positive 1/2. Well, that means that if I perform the sum on this term, I can perform the sum on the partial fraction decomposition of it, and I can factor out a 1/2, which is just going to leave me with the sum of the difference of 1 over n minus 3 minus 1 over n minus 1. And this goes back to what I was saying before, that a lot of partial fraction decompositions of sums lead to telescoping sums. What do we have here? Well, I'm looking for the sum of an minus j. Is that going to be anything here? Well, the bigger of the denominators is the negative 1 term, right? Because negative 1 is bigger than negative 3. So let's go ahead and define an to be negative 1 divided by n minus 1. And how many steps away from negative 1 is negative 3? Well, it's going to be 2 steps away. So an minus 2 would end up being negative 1 over n minus 3. Well, that tells me I can use my summation formula for a telescoping sum with j being equal to 2. And what does my formula actually tell me this should be computed as? It should be computed as a n minus 1 plus a n minus 2 plus c. So now I'm just going to have to figure out what is an minus 1 plus an minus 2. It ends up being, well, a1 is negative 1 over n minus 1, so an minus 1 will be negative 1 over n minus 2. And an minus 2 is, of course, negative 1 over n minus 3. So that ends up being my summation of this remaining term. But I can, of course, do the harmonic number version of this if I want to, and then I would just end up with 1/2 harmonic number n minus 4 minus 1/2 harmonic number n minus 2. I don't like that as much. Here's my negative 1 over n minus 2, negative 1 over n minus 3 term that I came up with earlier. And then the 1/2s, recall, were my coefficient if I go all the way up to here. Okay, but what have I just computed? I've just computed the sum, right? This was the sum of the remainder term. There was other terms, and if I scroll back up a little bit to when I actually performed my polynomial long division here, I did have a negative 2n minus 2 that I will have to sum itself. So if I sum negative 2n minus 2, how could I do that? Well, I could factor out a negative 2, and then it's the sum of n plus 1. But n plus 1 is actually n following factorial 1 plus n following factorial 0. And my second power rule for sums tells me that I can just add 1 to the power and divide by that new number, add 1 to the power and divide by that new number. What is n following factorial 2? Well, it's n times n minus 1, and that 2 is canceled with that, and then it's also distributed over here to give me a 2n because n following factorial 1 is just n. If I rewrite this, a little simplification, I can call it negative n plus 1 times n. So that term needs to get added to what I just computed below with the 1/2s and the 1 over n minus 2 and 1 over n minus 3. If we add it all together, here we have it negative n plus 1 times n minus 1/2 times 1 over n minus 2 minus 1/2 times 1 over n minus 3 plus c. Now, it really is fascinating that we were able to come up with a closed form solution for that summation using partial fractions, as well as some of our other power rules. Really, really fascinating. Anyway, we're going to stop there for today. I hope it was fun. It's always fun for me to do these. Next step will be convergence tests for improper integrals. Yes, we're headed back to improper integrals. Anyway, I'll see you then. Bye.